Directional derivatives and gradient. We get to learn another new symbol today.
Did we do 57?
We didn't do 57. All right, so the directional derivative and the gradient, that's what we're going to talk about today. The gradient is going to, the idea of a directional derivative and the gradient, we're going to use that a lot for the rest of the year. So what we're interested in, let me draw our axes here, is we have a surface and we've been talking about the rate of change of our function as partial derivatives. So our partial derivatives give us the rate of change of our function. So here's our surface. Our partial derivative with respect to x gives us the rate of change of our function at a constant y. So we're in the direction of the x-axis. Or the partial derivative with respect to y gives us the rate of change in this direction. But what we're interested in today is if we have some vector down here, and we'll say that this is a unit vector. We're going to call this u. We want to know the rate of change of our surface in the direction of that vector. So up here, as we move from, we're going to say x0, y0 in the xy plane to some point xy, we want to know how our function changes in the direction of this vector. So that's what we're interested in today. And our partial derivatives are a special case of the directional derivative, because we're looking at the direction we're looking at is in the y direction or in the x direction. So that's what we're going after today. So let's call this surface, this is some function f of xy. And we're going to define the directional derivative as we call this the directional derivative, and our notation for the directional derivative is the derivative in the direction of u of f of xy equals the limit as we're going to say delta t approaches 0 of f of x0 plus delta t times a, and we're saying our vector here, our unit vector, u is a vector this is our vector is given to us by AB, and we're going to assume that our vector is a unit vector.
But it doesn't start at 0, 0?
Doesn't start at 0, 0. It's just a vector. It's a unit vector unit, it's one, our length is 1.
Yeah. But I'm just confused with this point, so if this A, B, that's
So from x to x0, if we subtract those two, we get a, and y to y0, we get b. Our directional derivatives, so as we move from x0, y0 to xy, it's x0 plus delta t a, comma y0 plus delta t b, minus f of x0, y0, and that's all over delta t. And this is our directional derivative. This should be at our point x0, y0. So this is how we define our directional derivative. We want to know how our function changes as we move from x0 to some point x0, y0 to some point xy, and as our increment of distance gets very, very small. So this is how we define our directional derivative. So it looks kind of like our definition of a partial derivative, but we have these delta t's in the x and the y kind of mixed together. We could, given a surface and given some vector, we could use this to calculate the directional derivative, just like we use a definition of the derivative to calculate the derivative in single variable calculus, where you have to go through all the delta t's and cancel and substitute. But we're going to simplify this because we have a nice way to simplify this. So let's go to our next page and we'll see how we're going to simplify this directional derivative. So we're saying that our vector, we said our vector is AB, and we're assuming that the length of u is 1. So we're starting with a unit vector. If we don't have a unit vector, we can always make it into a unit vector. Parametric equation for a line through the unit vector, if we're starting at point x0, y0, parametric equations for our line are for a line along u are x0 plus at and y0 plus bt. So that's for some parameter t. So we're just parameterizing the equation for this line. So if we're traveling along this line that goes through our vector, let me go back to our picture. If we're traveling along that line, as the parameter increases, we're going to be traveling along some curve on our surface. So this, if we express our function f of xy in terms of this parameter, we have what this does is make f of xy implicitly a function of t. So f of xy is our surface. So f of xy is also a function of t because x and y depend on our parameter t as we're traveling along that line. So what we're going to do is we're going to calculate we're going to calculate the partial of f with respect to t. And that's going to give us the derivative of our function along that curve on our surface. So if we take the derivative of f with respect to t as our parameters changing, as our time parameters changing, we're moving along the curve on the surface that we're interested in, and df dt is going to give us our derivative that we're interested in. So using the chain rule, now we know the chain rule for partial derivatives. We know that df dt equals df dx dx dt plus df dy dy dt. So our partial with respect to x, we were talking about any function, so that's just going to be df dx. dx dt from our parametric equation of our line is just a, plus df dy, and our partial with respect to y is just b. So this is how we're actually going to compute, how we're going to calculate our directional derivative. This gives us the derivative of our function in the direction of the vector that we're interested in. We express the vector as a line parallel to the vector as parametric equations, and as the time parameter increases, we're moving along the direction of the vector in the xy plane. So we're moving along the direction of the curve on our surface. So this tells us that the directional derivative in the direction of u of f is just the partial of f with respect to x of xy times a plus a partial with respect to y of xy times b, where a and b are the components of our vector. And we can rewrite this as, we can also write this as df dx a plus df dy b. So this gives us the rate of change of our function in the direction of our vector ab. And this is what we call our directional derivative. And if we define our vector, if our unit vector is defined by the angle it makes with the positive x-axis, so we have a vector and we know the angle it makes with the x-axis, we can write this as our partial derivative with respect to u of f is f sub x cosine theta plus f sub y sine theta. If our vector is given to us by an angle with the positive x-axis. So a couple of important things about the directional derivative. We have an infinite number of directional derivatives. We can decide to take the directional derivative in any direction. So we can, for any possible value of our vector that we're interested in, so we can have an infinite number of directional derivatives, not just one directional derivative. And our directional derivative is, again, it gives us the rate of change of our surface in a specific direction. Our partial derivatives give us the rate of change of the surface in the x direction or the y direction. This directional derivative gives us the rate of change of our surface in any direction. The one that we're usually going to calculate with, the one we're interested in, is this one. Now, if we look at this expression for the directional derivative, df dx times a plus df dy times b, and a and b are the components of a vector. What kind of vector quantity does this look like? This looks like a dot product. If a and b are x and y components of a vector, df dx and df dy, if we think of those as components of another vector, this looks like a dot product. So we could say that our directional derivative of f, if we make a vector out of our partial derivatives, this is the dot product of that vector that we make out of our partial derivatives with our vector that gives us the direction that we're interested in. So the directional derivative comes up in so many different contexts. We want to come up with a way to make our computation easier. If we could use this dot product representation, we could use what we know about vectors to make our computations a little easier. So we're going to make a definition involving this particular vector. So we're going to define the gradient vector. And the gradient vector is our big idea of the day, the gradient vector. We call it del, and there's our new symbol. It's an upside down triangle. It's an upside down, we call it del because it's an upside down delta. So del of f of xy equals df dx I plus df dy j. And if we have a three-variable function, del of f of x, y, z is df dx I plus df dy j plus df dz k. This is our gradient vector. And we call del is it's what we call an operator. So del has no value by itself. It has to operate on a vector. And we define del, the operator, and the three equals means defined, as d dxi plus d dyj plus d dz k. Del has to operate on a vector to have any meaning. These partial derivatives by itself don't have any meaning. So we have to operate on, we have to operate on a function, not a vector. We have to operate on a function to get a vector. So del has to operate on a function to have meaning. Del is also known as the gradient. So we can, sometimes you'll see it written, it's an older, I think a little older notation. Del f is the same as grad f. And this means gradient. So if you see this notation, it's the same as the del notation. It's the same thing. So using this notation, our directional derivative in the direction of a unit vector u of f of xy equals del f of xy dot u. And we're assuming that the length of u is 1. So we're looking at, we're interested in the direction, the same direction as a unit vector. So if we don't have a unit vector, we need to make it a unit vector. We need to normalize our vector. So this is a nice, this is the shorthand way, this is the convenient way that we're going to find our directional derivative. We're going to find the gradient of our function and take the dot product of the vector that we're interested in. Now, a couple of important things about the gradient vector. The gradient vector gives us a vector in the xy plane, not a vector in space. So if we're talking about a two-variable function, our gradient vector is in the xy plane. We're talking about a surface, but our gradient vector is in the xy plane. It doesn't point up or down. In space, when we have a three-variable function, it does have a z component. But if we're talking about the gradient of a two-variable function, our gradient vector is in the plane. So it points some direction in the xy plane. So let's use the gradient. Let's calculate some directional derivatives. Let's look at a few examples. Any questions before we go on? All right, here are our examples. Let's say we have a function g of xy equals the square root of x squared plus y squared. And the vector that we're interested in is v equals 3i minus 4j. And our point is 0.34. We want to find the directional derivative of g in the direction of v at 3, 4. So we want to know how this function, we want to know the rate of change of this function in the direction of this vector 3i minus 4j at the point 3, 4. Well, the first thing we need is a unit vector. Our directional derivative, dv of g, is going to be del g dot v over the length of v. We need a unit vector. So let's calculate our gradient first. Del g is going to be the partial of our function with respect to x in the I direction. So what's a partial derivative of this function with respect to x? One half over square root of x squared plus y squared times 2x. So the 1/2 and the 2 cancel, and we just get x over square root of x squared plus y squared in the I direction, plus, and this is symmetrical in x and y, so our direction, our partial with respect to y is just going to be y over square root of x squared plus y squared in the j direction. And our unit vector, v over the length of v. The length of v is just the square root of 9 plus 16. So that's 5. So v over the length of v equals 3/5 I minus 4/5 j. So our directional derivative del g dot v over the length of v is going to be x over the square root of x squared plus y squared times 3/5 minus y over the square root of x squared plus y squared times 4/5. And we're interested in the point 3,4. At 3,4, this equals, if we plug our points in, we get negative 7/25 if we plug in 3 for x and 4 for y. So what this tells us is that at point 3,4, g is changing minus 7/25 units for every unit that we move in the direction of v. That's what the directional derivative tells us. As we move in the direction of v, our function changes minus 7/25 units for every 1 unit we move in the direction of our vector.
Would you say that again?
What this tells us is that our function g is changing by negative 7/25 units for every unit we move in the direction of v.
Changing 7/25 unit for
U
every
units. Whatever our units are. If we're measuring in, depending on what our function is giving us. If our surface were in x and y and we're measuring in meters, so our function would be changing minus 7/25 meters per meter that we move in the direction of v. All right. Before we finish, I want to give you some important properties of the gradient that we're going to expand on Monday. So properties of the gradient. One, if del f equals 0, then the directional derivative of f equals 0 for every vector. So if our gradient is 0, the directional derivative in any direction is going to be 0. This one, the next one is important. Del f gives the direction of the maximum increase in f. So if we find the gradient, we find the gradient of our function, that vector points in the direction of the maximum rate of increase of our function. And the maximum value of the directional derivative is the magnitude of the gradient. So del f points in the direction of the maximum increase in our function. And remember, our gradient is a direction in the xy plane. So it's like a compass heading. So if you think of your function as a hill and your gradient as a compass heading, your compass is going to point in, if you take del f, your compass heading is going to be the direction where you would climb the hill the steepest. That would be the compass heading that would give you the steepest ascent of your hill if you're thinking of your function as a hill. And our third one is the opposite of this. Negative del f gives the direction of minimum increase. And the minimum value of the directional derivative is given by the opposite, the negative of the absolute value of the gradient. Number 2 and 3 are going to be extremely important moving forward. That the gradient gives us a direction of maximum increase in our surface. And if number 1 is going to be very useful as well. And we're going to be using the gradient for lots of different things as we move forward. So we need to be, very familiar with the idea of the gradient and how we find the gradient and what it tells us. And we need to be familiar with these two ideas. We'll work with the gradient a little more on Monday, and we'll do a couple of different kinds of problems using the gradient and the directional derivative. All right, homework. All right, there you go.